Hello, my name is Jeremy Seek. I'm a professor at Indiana University, and today we're going to be talking about how to write proofs in Deduce, and this is part 2 in a series that introduces some of the basics of writing proofs in the Deduce proof language and then using the tool to check those proofs. We're going to just dive into some more logic. So we're going to start off with talking about the OR, logical operator, sometimes called disjunction, and we're going to show different ways that you can the way you can prove something that's an OR formula, or how you can use something that's an OR formula. So let's dive right in and show an example of this. So in fact, there's a simple property here that we can prove, which is that OR commutes. Okay, so let's say we have a P and a Q, and if we know that P or Q is true, then it should also be the case that Q or P is true, right? So the ordering within an OR shouldn't matter, okay? And maybe just to quickly review the meaning of OR, it really is saying that at least one of the things, of the parts, needs to be true, right? So P or Q says that, well, at least one of P or Q is true, okay? Maybe both, maybe one, but definitely not zero. So they can't both be false, okay? All right, so let's go ahead and dive into this proof. I'm just going to put question mark there to begin with to tell Deduce that that we're doing an incomplete proof. Looks like I had a typo here. Deduce is telling me that it's expecting the keyword then instead of the. Okay, so let's correct my typo. Okay, so now Deduce is giving us some. It's telling us, okay, here's our goal that we want to prove. And it's giving us some advice. Of course, we talked about this last time. When you have an all formula to prove, your sort of plan A, the first option that you want to go with for proving that is to just pick, let P and Q be arbitrary, placeholders for any Booleans. Okay, and then if we can go ahead and prove the rest of the formula without knowing anything about this P and Q, then it'll apply to all of the P's and Q's. Okay, so now we've gotten rid of the all, and now we've got a goal that's an if-then statement. And again, as we learned last time, if you've got an if-then that you're trying to prove, you want to go ahead and do an assume. Right? You want to assume the premise, right, which is P or Q. And then we're going to try to prove the conclusion. Okay, so what's the conclusion of our if-then? Well, it's just Q or P. All right, so that's, in some sense, what we've done so far is a review of last time, dealing with all and if-then. Now we're at the new part here, where we've got a goal that is an OR. Okay, so how do we prove something that's an OR? And we also have a given, a fact that we already know is true, that's an OR. We know that P or Q is true. Okay? So the main way that you can use an OR is with something called the cases feature of Deduce. So I can say cases, and then I can give it an OR. So the premise is a proof of P or Q, so we can give that to our cases. And then now we're going to have a case for every one of the alternatives in the OR. Okay, so we can write P. I'm going to do lowercase p as a label for referring to P, and in case lowercase q is the label for Q, and then we'll keep going with our proof like that. See what Deduce tells us next for advice. Okay, so our goal is still Q or P, But now we have a new premise, okay? We know that P is true, okay? So here, now we're about to learn, like, when you want to prove an OR, how can you do that? And in Deduce, if you just prove one of the parts of the OR, then that's implicitly sort of good enough to prove the OR. So if I just put P there, that's going to work. Okay, and now Deduce has already moved on to the next question mark, right? So Deduce was perfectly happy with Q here. Okay. If I want to be a bit more explicit about the proof, make it maybe make the proof easier to read, I could say something like, I can use a conclude statement here to sort of reiterate what the current goal is. Okay, so Deduce was telling us what the goal was, but it didn't actually appear in the text of the proof. And sometimes it's nice for your readers just to kind of remind them of where you're headed, right? So here we said conclude, and then we're going to put the reason, which is that P is true. Okay, so Deduce was happy with that, and now we're moving on to the other case. This other case is similar, except now we know that Q is true. Okay, that's down here, one of our givens. Okay, so we can conclude that Q or P is true, but this time we can use by Q. All right, and that completes our proof. Okay. So this is a pretty common pattern. You've got an OR that you've already proven true. You then break it down into cases, and in each case you get to assume, you get a given that the part of that OR is true. And then in each of these subproofs here, we're going to prove our goal, right? So when you have cases, you just have to keep proving your goal over and over again, but you get to use different. You've got the different facts to use each time. Okay, maybe one other thing to mention here is that sometimes the actual formula is the same length as the label, okay? When that happens, if you want to, you can leave off the label, and instead of referring to the formula, the thing that you know is true by label, you can refer to it by the formula itself. So you can say recall and then give the formula, and Deduce will go and look up that to see if that formula is in one of the things you've already proved. It's one of the givens. Okay, so that worked there. Okay, so that was OR. The next thing I want to talk about is the formula false. Okay, and false plays an interesting role in logic, especially because there's this thing called the principle of explosion, that if you somehow have maybe through a contradiction or something, you've proved that false is actually true. You've proved false, then the world explodes. Then it's like from then on, it's like you can prove anything. Okay, so that's the principle of explosion. I'm not making this up. This is a well-established principle in logic. So here we're going to use an example of that. So suppose we have an if-then, but what we're going to put in our premise is actually the formula false. Okay, and then in the conclusion, we're going to put something just as ludicrous, that 0 equals 1. Okay, and it turns out that this if-then statement here is actually true. Okay, right? And if you recall that whenever the premise is false of an if-then, then you're always then you're true. Okay, but we're going to do this as a way of sort of showing the principle of explosion. Okay. So as usual, if you want to prove an if-then, you Deduce is saying, hey, you forgot to import the unsigned integers, because I was using an unsigned integer, the 0 and the 1 here. So I'm going to add that import. Okay. So right, as usual, if you want to prove an if-then, you assume the premise. Okay, so now we actually have false as one of our givens, okay? So kind of one way to think about the situation where you have a false in one of your givens is that we're currently sort of considering a hypothetical situation that in fact can't exist, okay, cannot exist, okay? And so here, but once you're in one of these, situations that cannot exist, sort of the rules of logic sort of go by the wayside, and you can prove anything from the false. So we can say we call false here to prove that 0 equals 1, okay? And indeed, deduce accepts that. Now, most of the time, you're not going to just have the formula false kicking around. Instead, what will happen is you might have some complex expression, and then you enter into some cases, and then in one of those cases, there's something that contradicts this big expression that you know is true, and so then you're able to derive false from that, and then from that you prove your goal, whatever your goal is. Okay, you then have sort of a get out of jail free card, because you've just shown that you're in a hypothetical situation that it doesn't exist, it's bogus. All right, sort of continuing on the theme of like false and sort of negative kinds of things, let's go ahead and talk about not, okay, logical not. So here what I'm going to do is we're going to do an example where we prove one of the variants of the De Morgan properties, okay? So you may vaguely remember this from school. So we have a P and Q, and if not P or Q is true, then it's the case that not P and not Q are true. Okay, we're just going to do this one direction, that not P or Q implies not P and not Q. Okay. Okay, let's see what deduce tells us to do. Okay, we've got an all formula that we're dealing with. So as usual, we'll start out with arbitrary. Let's go ahead and paste that in. And we've got an if-then. So we'll go ahead and assume that the premise is true. And let's see where we're at here. Okay, we're trying to prove not P and not Q. Okay. So we already talked about how to do an and, how to prove an and, right? We have to prove both parts, okay? So let's go ahead and do that. I'm going to, we're going to do some forward reasoning now, or actually, I'm sorry, backward reasoning. We're working backwards from this goal, and so we're going to prove the parts. So we're going to prove not P, right? We're going to do a proof of that. And then after we're done with that proof, then we're going to prove not Q. Right, these are like going to be these subproofs. And then from that, we'll actually be able to conclude. Actually, let's go ahead and put sorries here to say, hey, we're going to skip those proofs for now, and we want you deduce to keep checking past those points in the proof. And then down here, to conclude, right, we want to conclude our conclusion there by, and then we can recall these two formulas, right? So we call not P, and then we're going to use a comma, right? We use a comma because we're proving an and. We're putting together these two different proofs and the not P there. Okay, so let's see if what we've got makes sense so far. Deduce says yes, we have a valid proof, but we do have these unfinished subproofs that we need to work on. Okay, So let's go ahead and dive in. Okay, so we need to prove not P. Okay, so the next thing we can learn about is sort of like, how do you deal with not, or how do you work with not in deduce? Okay, so one thing to realize is that deduce, when deduce sees not P, it thinks that's equivalent to if P, then false. Okay, this is sort of a standard sort of way of thinking about not. Okay, thinking of it in terms of implication. Okay, right. So if deduce thinks about not as implication, as an if-then the right way to prove a not is to go ahead and to assume the premise here, which is P. Okay, so we'll go ahead and assume P, and we'll see that deduce is happy with that. Right, we've just assumed P, and now we need to prove the conclusion, right, which is false. Okay. All right. Let's look at our what we know so far. What are our givens? We have P. We also have not P or Q. Okay. Now at this point, we should be thinking, how can both of these things be true at the same time? Right? And because, I mean, after all, if we know that P is true, that means P or Q must be true as well. But here we have this premise that says that's not true, right? So we're going to have some kind of contradiction here. Okay? So let's go ahead and sort of write out what I was just thinking, right? So the first step was that we know that P or Q is true, right? So we have P or Q, and we can do that by, we know that P is true, right? So we know that one of the parts is true. So that works out great. Okay, so now we have P or Q. Okay, so now we're in the situation where we literally have, a particular formula is true, and then that same exact formula with a not on it. Okay, so this is where contradict comes into play. So there's a feature called contradict, and we can just put the two formulas, okay, or the two contradictory proofs, right? So we have P or Q, and then we also have our premise, which is not P or Q. Those two are contradictory statements, and so deduce was happy with that as a proof. Okay, so we got our contradiction there. And contradiction, right, we were trying to prove false, right? So maybe let's go ahead and, we will conclude false by contradict, right? We can make that extra explicit if we want to. I mean, you don't have to, but if you want to, you can. All right, so when you have a contradiction, that's one way to prove false. Okay? Okay, now we're going to have sort of a similar situation down here. We want to prove not Q. It's going to be a very similar process here. Oops, I hate when the indentation gets messed up. Okay, so what are we going to do? We're going to assume Q. And then, again, we can prove that P or Q is true. But this time, it's because we know that Q is true, right? You notice that I tell deduce to process the file over and over again, right? And deduce is super fast, at least on relatively small files. And it can give you advice about what to do, and you can sort of incrementally check that each statement that you've typed in is correct so far. So I prefer to find out right away if I made a typo instead of waiting and then having maybe lots of lines of new proof that might have typos in them. Okay, so we need to prove false. Okay, so maybe we want to do another contradiction here. So contradict, we call P or Q, and then again the premise is not P or Q, right up here, not P or Q. concludes our proof. So that was the proof of this particular variant of De Morgan's rule. Okay. I think that's actually a good place to stop for now. That's after this, we're going to, the next part, we're going to look at doing some equational reasoning about numbers, and then do some reasoning about things like linked lists. So lots of interesting stuff to come.